video, we're going to look at displaying and summarizing quantitative data. So if you'll recall, in the last chapter, we talked about different ways to display categorical variables. Take a few seconds to think about some of those ways. First, we had bar charts. And then we talked about pie charts, segmented bar charts, and mosaic plots. We also looked at side-by-side bar charts and side-by-side pie charts, which we can use when we have two categorical variables. For quantitative variables, we're going to look at different ways to display our distribution. And some of those graphical displays we can use for quantitative data include histograms, stem and leaf plots, box plots, dot plots, and cumulative distribution graphs. Also known as ogives. So with categorical variables, each category was its own natural pile. When we're dealing with quantitative variables, there's no obvious way to choose those piles. So we need to determine our own way to pile all the data up. So we're going to slice them all up into equal width bins. And then what we're going to do is count the number of cases, or the frequency, that fall into each bin. Okay, the bins, together with these counts, give the distribution of the quantitative variable, and they also provide keys to creating a histogram. So here's a picture of a histogram. Take a few seconds and pause the video and write down what you think the histogram is trying to show. What do you notice, and what story is the graph telling you? The histogram here is actually showing us the number of earthquakes with specific magnitudes. So we can see here the magnitudes all the way from a little less than 4 all the way up to past 9. And then of course the frequency. So the number of earthquakes that had, for instance, magnitude 7 or magnitude 6 and so on. Okay, so there were 1,017 earthquakes known to have caused tsunamis, and that's actually what these represent. And this dates all the way from records from 2150 BCE to the present time. And we're going to look at how to construct those histograms. So while categorical variables naturally have spaces between the bars, like in a bar chart, any spaces in a histogram are actually gaps in the data. So we normally will have the bars touching each other unless there's a gap. Okay, and the gap just indicates that it's an interval where there's no values. Sometimes, as we did with bar charts, we made relative frequency or relative bar charts. We're going to also make relative frequency histograms. And if you'll recall, relative just means we're going to replace the frequencies with percentages. Okay, so here we have a relative frequency histogram of the same data, the hurricane or the earthquakes and their magnitudes. So what do you notice about these two graphs? And if it helps, I'll take this one and put it side by side so you can compare them. Okay, what do you notice about them? If you notice that they are the same shape, the shape didn't change at all, you are correct. The only thing that's different is for a histogram, we have our frequencies on the vertical axis, whereas for relative frequency histograms, we have percents on this axis. But it did not change the shape. It did not change where we think the center of the distribution is, or how spread out it is, which is what we're going to look at in this chapter. We're going to construct a histogram by hand, and then I'm going to direct you to a video that I'm going to place in Canvas, which will show you how to construct a histogram using your TI-84 Plus. Okay. So take a second to pause the video and read the problem. For an agility test, fourth grade children jump from side to side across a set of parallel lines, counting the number of lines they clear in 30 seconds. And then here are their scores. We're going to construct a histogram, so a picture of what we see there for our distribution. So the first thing we want to keep in mind is we need to figure out like spacing. How are we going to take this data and put it into piles that are the same width? So in order to figure out the width, we're going to take the highest value, the maximum, which appears to be 29. That looks like it's the highest. And we're going to subtract the lowest, which looks like it is 12. Okay, so we're going to take the max minus the min, and then I need to figure out how many bars I want. So I want, a good rule of thumb is to have anywhere from 5 to 15 bars. If you have less than 5, you'll have really tall bars. So they'll be like skyscrapers, and it won't really be able to tell us too much of a story that's going on. And if you have too many bars, it comes out, the histogram looks like pancakes. They're going to be very flat. Again, they're not going to indicate any important features in the distribution. So I'm going to divide by 5. I want about 5 bars. Okay, and if I do 29 minus 12, that gives me 17. And then 17 divided by 5 is like 3.4. Now, I could be messy and I could have a width and use 3.4, but I'm just going to round down to about 3. If I had gotten 3.5, maybe I would use it, or I just might round up to 4. It's really your choice. Okay, so that means that I'm going to take my lowest number, and I'm going to create a table here. So we're going to have what's called the class, or classes if you prefer, and then the frequency. So I'm basically making a frequency table. And remember, frequency just means counts. So here's where I'm going to create the piles to put the numbers in, okay? My lowest number, again, is 12, okay? So for my first pile, I'm going to go from 12, and I'm going to add 3 to that. So 12 plus 3 gives me 15. So what that means is anywhere in this table where I have the number 12 through the number 15, I'm going to count how many times that occurs. Well, I only see one number from 12 to 15. It's just the number 12. So my frequency there is just 1. To get my next bin, I'm going to start at 16 now, and I'm going to keep adding 3 to it. So 19, okay? And I'm, again, going to count how many numbers are from 16 to 19 inclusive. So here's one. Just going to color these in here. Anywhere I see a number from 16 to 19 inclusive. And it looks like I've got 5 numbers there. And I'm going to keep doing that. So my next number would be 20, and then I'm going to add 3, and then 24, and add 3, and then 25, and add 3. Okay, and I can stop there because I don't have any numbers greater than 31, right? My highest number was 29. I need a bin to fit the 29 in though. So you're, again, just going to count, and you should end up with the following. And it's always a good idea to check, right? So I can add these up. And when I add those, I get 25, which is how many data points I have. I've got 25 different numbers, okay? So these are my bins. And my bin width is actually considered to be 4, okay? Because when I create my histogram now, you've got your frequency on the vertical axis, and on the horizontal axis, I have the number of lines, right? Like it's number of lines that the children are jumping over. The classes are going to go on the bottom, right? Frequency goes along the vertical. So the frequency is easy. I just have to go to 10. So I'm probably going to count by twos, and I'm going to try to make them equally spaced. And then I'm going to here have a little break in the graph, right? Because I'm not really starting at 0, I'm starting at 12. And my bin includes every number from 12 to 15. So I'm going to have my first bar here start at 15. The next one's going to start at 16. So I'm using these numbers here to create the left bound of each of the bars. Okay, and again, make them equally spaced. As equally spaced as humanly possible. And now all I'm going to do is just draw a bar up to the frequency. So I know for 12 to 15, it's going to be, that's a little bit too high. There's only one, right? So I'm just going to go maybe till about there. Okay. And then for the next bin, I'm going to go up to 5. And then my next one is going to be 10. As you can see, there's no spaces here between the bars like there was on a bar chart, unless there just happened to be a gap in the data. So I would know that because I'd have a 0 under frequency. The next one's going to go up to 7. And then the last one is going to go up to 2. Okay, and there you go. You got your 5 bars, you have your histogram. Now, when you create it on the calculator, it may look a little bit differently because your calculator sometimes auto-determines what the classes will be. Because the calculator does do all the bulk of that work for us, all the little calculations that we did here, the calculator determines what the size should be there, but you can manipulate and change it to make it look like this. But there's various ways you could create a histogram representing this data. So I could have used maybe 6 bars or 10 bars if I wanted, it doesn't matter. But again, the general rule of thumb is to have anywhere from 5 to 15. Okay, so that was our picture, right? And of course, we always need a title, so you don't want to forget that. We're going to look at, once we have that picture, okay, what do we do with it? So we want to be able to pick out important things from it, important features like center, shape, spread, and things that we're going to be able to look at that are going to tell us a lot. Okay, but before we get to that point, let's look at some other graphical displays that we can use for quantitative data. So here we have 2 graphical displays. The one you're familiar with, we've got a histogram, and it represents the pulse rates of 24 women, okay? Here's a different type of graph you can use for quantitative data, and it's called a stem and leaf plot. Okay, and basically you have here numbers created using stems and leaves. So the number 88, for instance, the 8 on the left is called the stem. So we have the stems over here on the left. And then on the right is the leaves, okay? So when I read this, I know that that's not the number 8, it's the number 88. So it's 88 beats a minute. This would be 80 beats a minute, and another 80, and another 80, and another 80, and then I've got 84, 84, 76, 76, 56, okay? So what are some things you notice or observe about both of the graphs? Is there an advantage to using one graph over the other? If so, talk about like why that would be. So take a few seconds, pause the video, and do some reflection and think about advantages, disadvantages. Okay, so what do I notice? I notice that both of these graphs show the pulse rates. However, if you notice, the stem plots actually show the data values, whereas that's missing in the histogram. Histograms provide an easy to understand summary. They're pretty easy to make. Stem plots can become very tedious if you have a large set of data, okay? But we can see the data values there. So histograms provide an easy to understand summary. And stem plots show the data values, whereas histograms don't. Here's another type of display that we use for quantitative data. It's called a dot plot, so it's made of all dots that represent the data points. Dot plots are very easy displays to make because you simply just place a dot along the axis for each case in the data, okay? What do you think this dot plot tells you? Take a second to think about it and then come back to the video when you're ready. So this dot plot actually represents the Kentucky Derby horse race, and it shows the time that it takes for each of the horses to win a race. Okay, I notice in this one there are some extreme values, right? There's a gap in the data, so why would that be? These could be considered outliers because they're further away from the rest of the data, or it's just a different cluster of points. We've got two clusters, and there's a reason that there's a gap in the data. So here it shows the time it took for each horse to win a race. In this graph, I notice there's some extreme values. And I also notice that there's a gap in the data. Okay, and a lot of times those gaps or unusual features are the interesting part of the data that you're looking at. Okay, other times they could be a mistake, but you never want to throw away values right away because they could hold a lot of interest in what we're looking at. So one of the shortcomings that histograms, stem and leaf plots, and dot plots, the three we've talked about so far, all have is that while they can show where the data are dense, they don't make it easy to tell with much precision just how many data values or what proportion of all the data lie in any particular interval, okay? So here's a histogram, and it shows the distribution of the ages of 100 US senators at the start of the 117th Congress. And there's a couple labels missing here, so I apologize. This should be right here, 30, and then this is 40, 60, sorry, 50, 60, 50, 60, 70, 80, 90. So we have the ages, and then we've got the US senators, okay? Can you tell exactly how many senators are in their 60s and early 70s by looking at the histogram? it's kind of hard to tell, right? What we can do is construct a different type of graph to look at this. So if we order the ages from youngest to oldest, in statistics we just call that ranking. We're going to position a senator holds in the order from 1 to 100, where the youngest is ranked 1 and the oldest is ranked 100 against the ages. Okay, so here we have the age rank and the ages. So the youngest senator, for instance, I can easily pick out right here, is between 30 and 40. And the oldest senators, right, are between 80 and 90. How many senators are between 60 and 75 years old? Okay. So one way to do this is to pause the video, take a look at the graph, and then unpause when you're ready so you can get a clear picture of it. And then we'll kind of talk about it. Okay. So one way to do this, right? I'm looking for the number of senators between 60 and 75 years old. So kind of like right about there. Okay. It's easy to count how many senators are younger than 75 because I have just a few that are older than 75, right? Like a 76-year-old looks like they rank about 90th. Okay, so that would be like 76 and their rank would be 90. So that just tells me that there's 89 younger senators than 75, right? Because they're ranked 90. Okay, so there's 89 senators younger than 75. And again, I know that. I'm going to put in parentheses here because a 76-year-old ranks 90th. So there's 89 younger senators, right? So that tells me there's 89 of these on this side. Okay, so I need to figure out this. So how can I get that? Well, I can also look here. Okay, someone that is 60 looks like they're ranked at about 30, right? So that would mean that there's 30 senators younger than someone that's 60. Okay, because a 60-year-old senator is about the 31st. It's kind of hard to see here, but that little dot right there. So there's 30 senators younger than 60 because a 60-year-old senators are 31st to the 36th. Okay, so now if I want to figure out this middle part here, like how much exactly is right in here, I could just take 89 and subtract 30. So therefore, 89 minus 30 equals 59. So there would be about 59 senators that are in their 60s and early 70s. The graph that we just used for that, where we replace the ranks on the vertical axis with the percentages, gives us what's called a cumulative distribution plot. Sometimes it's called an ogive. The graph also allows us to compare distributions that might not be the same size. So that's one of its other advantages. Like if I wanted to look at the US representatives and the US Senate, I could create a cumulative distribution plot to look at that, where you can compare the age distributions of both groups. Okay, so what are some features that you can tell by looking at this? About 28% of the representatives are 50 years or older, while only 13% of the senators are that young. Okay, that's something that I can tell by looking at that, right? So you can see here where they have it blocked off. About 28% of the representatives are 50 or younger. Okay, so that's the representatives right here. So 50 or younger. Okay. And then 13% of senators are that young. So here's the senators right here. Okay. So So that just tells us that, there's a larger, and that should be 13%, not 31%. There's a larger percentage of representatives that are younger than senators of that same age. So all these graphs represent graphs you can use for quantitative variables. But before you construct any of those graphs, you always want to check the quantitative data condition. And it just says that the data are values of a, surprise, quantitative variable whose units are known. In the next video, we're going to look at actually how to describe the distribution, and we're going to look at 4 things: shape, center, spread, and potential outliers. Let me know if you have any questions with this part of the video.